Have you ever wondered how computers can read handwriting? Even terrible handwriting like mine? Would you believe that there's actually a lot of really cool math that goes into doing this? If that sounds interesting to you, then keep watching. In this video, I'm going to talk about one mathematical technique that you can use to make a computer program that can read handwritten numbers. Do you remember how you learned to read letters and numbers? If you're anything like me, then you probably had to look at different letters and numbers a whole lot of times before you remembered which one was which, to figure out what letter someone wrote every time. Well, guess what? Computers can learn in the same way. If we provide it with a lot of examples of handwritten letters and tell it how to learn, a computer can get pretty good at reading your handwriting. This is called machine learning because a machine, the computer, is learning how to do something, read your writing. One of the hardest parts is telling the computer how to learn, but thankfully there are a bunch of methods that smart people like you have already come up with. We're going to look at one of these methods called Knearest Neighbors. Before we think about handwriting, let's take a trip to Blue and Redville to learn how Knearest Neighbors works. In Blue and Redville, there are two kinds of houses, blue and red. People with blue houses like to live next to other people with blue houses. People with red houses like to live next to other red houses. We can see a kind of natural border that forms between these two communities. So if new houses are built far away from the border, we can easily guess what color they should be. If it's in the blue area, it should be blue. If it's in the red community, it should be red. But what if we have a new house that's right on this border? Then it's a lot harder to tell what color they should be. One way we could do this is to take a vote from its three closest neighbors to see what color they think it should be. So we'll do that with this one. First we have to find out what are the three closest neighbors. And then we take a vote. And because more of the neighbors want it to be blue, we'll make this house blue. And we can do the same thing with our other house. We find the closest neighbors, we take a vote. But this time, because more of the neighbors think that the house should be red, we're going to make this house red. But how could we apply this to numbers? To do that, we're going to take a trip to a new city, 0 and 8ville. This time, our neighborhoods are now based on numbers, not colors. Their locations are now based on their shape. The more similar two images look, the closer they are in the neighborhood. So numbers at the border are somewhere in between an 8 and a 0. It's hard to tell. So how do we find out who the closest neighbors are? Well, to do this, we're going to have to look at how computers see pictures, like pictures of numbers. If we zoom in on this black and white picture of an 8 that I wrote, it becomes more pixelated. And if we zoom in even more, we see that it's made up of a grid of individual squares. These are the pixels. Each are a different shade of gray. The computer sees each of these colors as a number. The darker it is, the larger the number. And now all of a sudden, we can read this picture just like a book. It's just a long list of numbers. So how does that help us measure the distance between two pictures? Well, let's look at three of our handwritten numbers from 0 and 8ville. First one's an 8, the last one's a 0, and the middle one is one of the ones that are somewhere in between. We're not sure which number it is. And here's what they might look like as a list of numbers. So one obvious way we could compare these two is by subtracting each number in one from each number in another, one by one. Just like this. But that's a lot of numbers to keep track of. So we'll add them up to get a number that represents the distance between one list of numbers and the other. In this case, we get 7. This is called the one norm, or the Manhattan distance, between these two lists. This is a way that mathematicians measure the distance between two lists of numbers just like we did. It's called the Manhattan distance because in Manhattan, part of New York City, all the streets are in a grid. So to get from one place to the other, you have to go straight in the side-to-side direction, and then straight in the up and down direction. You can't just go straight from one house to the other. You'd have to walk through some skyscrapers. So just like in our pictures, we can describe where the houses are on the map with a list of numbers. Here, we'll call the question mark house 0, 0, and the blue house 5, 2. So to find how far away they are from each other in each direction, we can just subtract the two lists of numbers from each other. So we get 5 in the side-to-side direction, and 2 in the up and down direction. We can add them together, and we get 7, which means we'd have to walk a total distance of 7 blocks to get from one house to the other. Now here's the cool part. Imagine that each pixel is a different direction, just like the two numbers that described where each house is in Manhattan. When we subtract the corresponding pixels from different images, we find the distance we have to walk in that pixel's direction. It's just that there are a lot more directions we can go. The first two pixels tell us how far to go in the side-to-side direction and the up and down direction, just like it did in our map of New York City. Then the next one, maybe that tells us how far we have to go walking straight up and down the building, if we could. But we run out of directions to go in the real world there. Since our world only has 3 dimensions of space, 3 numbers can describe a location. However, in Pixel World, there are a lot more directions. Even if you can't imagine how you would move in another direction, don't worry, I can. All you have to do is add up all the distances in each direction to get the total, just like we did to get 7 between these 2 numbers. So now we'll find the distance between the unknown digit and our 0. Here, we see that because 7 is less than 60, our unknown digit is closer to the 8. All of a sudden, we can measure distance between 2 pictures. Alright, so we've learned a lot so far. Let's look back at it and put it all together. So, the first step in our process was called pre-processing. This is where we turned our picture of a handwritten number into a long list of numbers, also called a vector in math talk. We do this for every picture we have of handwriting, where we know what the number actually is. The next step is the actual machine learning. We learned about a method called Knearest Neighbors, where we identified a category of a new thing by asking the 3 closest things to it. By taking a lot of examples of pictures of numbers, we get a good idea of different neighborhoods for written numbers. Before we can use the neighborhoods to identify unknown numbers, we needed a way to measure what the closest pictures were. So we learned about using the Manhattan distance by subtracting 2 pictures pixel by pixel. And finally, we can get to the really good stuff, prediction. This is where we look at a new unknown image and we try to figure out what number it represents. So, to do our prediction, we went out and found 48,000 different pictures of handwritten numbers, along with a label for each number to tell us what number it really was. Then we converted each of these numbers into a list of numbers, just like we did earlier, pre-processing. We can train our computer to recognize different neighborhoods of numbers with this data. Then we use 14,000 more digits, these are the unknown numbers, to test out how well our program learned which digits were which. We can't use the original data because the program would always get it right, since it already knows what number it should be. It has the label. The last thing we did is to check how many of the testing pictures our program guessed correctly, how good it is. So this may all sound complicated, but we can do this in only one step, only one line of code, using a programming language called R. Let's talk through all the different parts of this line of code. First, we have the Knearest Neighbors function. This is the pre-written code that does the prediction, like we've talked about. All we have to do is give it the right data. Next, we have our training data. In this case, it is the 42,000 pictures of written numbers that we have. We know which numbers these pictures are supposed to be of. It's almost like the addresses of houses in a neighborhood. Next, we have the labels for our training data. This is like a directory telling the computer what color the house at a particular address should be, or in our case, what number the picture really is. For example, this picture of an 8 will be labeled as an 8, so the program can start to build its map of the 8 neighborhood. Then we have our testing data. These are the unknown pictures. We use the neighborhoods made by the training data to decide what label for each of these unknown numbers. Then, the last input to the KNN function is K, which we set to 3. This means that we decide on the label for an unknown picture using the 3 closest known pictures, the 3 closest neighbors. In this case, we chose 3, but we could have chosen any other number. Finally, on the left side of the equal sign, we have the prediction that results from running the knn function. This will be set to a list of labels for the testing data pictures. We can then see how many of those guesses are correct. In our example, this ends up being over 97%. That's really good accuracy. That means that for every 100 pictures that our program tries to recognize, every 100 drawings of a number, it gets less than 3 of those wrong. That's pretty cool. Thank you so much for watching this video. I hope you learned something and also found it interesting. If you like learning about math, computer science, and lots of other connected topics, I highly recommend checking out 3 Blue 1 Brown's YouTube channel. Thanks also goes out to Lieutenant Colonel Horton, one of my teachers whose final project inspired the topic for this video. If you were intrigued by this video and wanted to learn more about coding, I have great news. There are tons of resources for you. For this project, I used R, which is a language specifically designed for mathematical and statistical coding. But there are all kinds of other languages you can use for this topic, and many others. I recommend starting with Python. It's not as hard to learn as many other languages, but you can do a whole lot of different things with it. I attached a link in the video description to a free Python tutorial, which is a great starting point for someone wanting to start programming. If this seems a little too intimidating for you, I also attached a link to code.org, which has tons of different coding games for all kinds of different levels, from beginner to pretty advanced. These can help get you started coding too. That's all. Thank you so much for watching.